Hi everyone, this is going to be lesson number 5 on the topic of quantitative chemistry for GCSE chemistry students. In this lesson we're going to be putting together all of the ideas that we've encountered in the last 4 lessons of this topic, and we're going to be making use of those to perform calculations concerning reactants and products in chemical reactions. So we're going to be looking at calculating, for example, the amount of reactant required to produce a certain amount of product, the amount of product we can expect to produce if we have a certain amount of reactant, and we're going to be looking at various kinds of reactants and products, solids and masses. We're also going to be looking at solutions. We're going to be looking at gas volumes as well. So we've got quite a lot to get through. So let's get started here by taking a look at the learning objectives for this lesson. So once you've completed watching this lesson video, and if you're watching it on my website, as always, there's going to be occasions where the video will pause and questions will pop up that you can answer interactively. And also once you've completed the end of lesson quiz and the other learning activities on this lesson's page within the GCSE chemistry course, you should be able to do the following things. So we need to apply essentially what we've encountered so far. So we're going to be applying some of the things that that we've already talked about, the idea of conservation of mass and the ideas of empirical and molecular formulae, ideas of masses of reactant and product. The term stoichiometry essentially is a word which is used to describe, in chemistry, performing chemical calculations relating to the amounts of reactants and products either consumed or produced in a chemical reaction. And this will also include calculating the concentrations of reactants or products in solution in terms of mass per unit volume and molar amount per unit volume. So there's quite a lot to get through here, and then towards the end we're going to be looking at Avogadro's law of gases and applying it to calculating quantities of gaseous reactants and products. So lots to get through. Let's get started here. Now, I'm also going to be, towards the end of this lesson, going through some of the exam questions which some of my students have requested me to go through, and I have a number of you joining me live for this lesson via Zoom. I will be addressing some of the questions that you've raised during the course of the recorded segment of this video, and a number of other questions which are slightly more advanced and fall outside of the scope of GCSE chemistry. I'm going to be going over those in the Q&A discussion with you all towards the end after the recorded segment of this lesson. So those of you joining me via Zoom, hold fire for those. I will go through those. But there are a number of exam questions. There are 7 exam questions that I've identified, which I feel are quite good examples that if we work through, will demonstrate to you just how to perform these reactions as well. So I will be going through those. Now, as always, if you're watching this as a recording, if you have any questions, then you can simply go to this lesson's page if you're enrolled in the GCSE chemistry course, and you can either type your questions into the live chat where I will respond, or you can send me your questions as a private message, in which case I'll respond privately to your questions within 24 hours or so. If you're watching this elsewhere, such as on YouTube, then by all means ask any questions in the comments and I'll get back to you there as well. So let's start by looking at the concept of concentration. So concentration is a term which is used to describe the number of particles of a solute, meaning a substance which is dissolved in a solvent, per unit of volume of the solvent. So let's start with a basic activity here where we can distinguish between volume and concentration and some of the units which are used to measure these things. So let's start with this question here. Volume of liquids. There are 2 measures here which are appropriate for measuring the volumes of liquids. What do you guys think? I'm going to pause here and let you guys have a go at this. And again, as with all of the questions that I ask, if you're watching this as a recording, the video will shortly pause and the question will pop up allowing you to answer. So what do you think? All right, so it seems like most of you have hit upon the correct answer here. Yes, so the volume of liquids among these 4 possibilities would be measured in cubic centimeters or cubic decimeters. Let's try another one here. So 1 cubic decimeter, what is this equal to? Which of these 4 options is equal in volume to 1 cubic decimeter? Very good. So yeah, so it's 1,000 centimeters cubed. Let's try this one. So 10 centimeters cubed, what is this equal to? Which of these 4 options is equal in volume to 10 cubic centimeters? Okay, so it seems like most of you got this one correct as well. Well done. So it is 0.01 cubic decimeter. Now, the concentration of a solution can be measured in two of these four ways. So which two of these four options would be appropriate for measuring the concentration of a substance in solution? Okay, good. So this one would be appropriate, grams per cubic centimeter, and this one also would be appropriate, grams per cubic decimeter. What about this one? The concentration of a solution can be measured in which of these four units? Good. All of you got that one correct. Well done. So moles per cubic decimeter. Excellent. So the idea of concentration is that it is a measure of the amount of a substance which is dissolved in a solvent to make a solution. So let's quickly make a note of this, because we're going to be revisiting this concept in some of the examples which follow. And after I've made a note of the key ideas here, I'm going to make use of one of these simulations, or a couple of the simulations from the PHET website, just to give you a sense of what the idea of concentration actually means. So remember, the term solution, this is a mixture. And if you go back to our definitions of the ways that matter is categorized by chemists, you either have pure substances, which are elements or compounds, or you have mixtures of pure substances. A solution is an example of a mixture composed of two things: a solute, which is dissolved in a solvent. Now, typically the solute is, when you have it in the pure form, typically this will be a solid which is soluble, which can be dissolved in the solvent, which is a liquid. So what you have here is two different substances, one of them in the solid state, one of them in the liquid state, and when you dissolve the solid substance in the liquid, you form a solution. Now, within that solution, we refer to the solid that was dissolved as the solute and the liquid into which it was dissolved as the solvent. So the concentration of a solution in chemistry is a term which describes the number of, or the amount of, I should say, the amount of a solute dissolved per unit of volume in a solvent. So when we use the term amount here, the term amount, remember the standard unit of the amount of a substance in chemistry is the mole. This is the SI unit. This is the standard unit for amount of substance. But we can also measure an amount of substance by mass. And so we can measure a mass instead. This would be non-standard. So this would be, for example, in grams. So we can talk about the number of moles of solute dissolved per unit of volume. Now, volume can be measured in a number of ways, as we've seen. It can be measured in cubic centimeters, it can be measured in cubic meters, it can be measured in decimeters cubed. These are all units of measure of volume. Now, the typical unit of volume, which is used when we're measuring the concentration of a solution, is decimeters cubed, cubic decimeters. But we could just as easily talk about moles per cubic centimeter, or grams per cubic decimeter, or grams, or we could talk about kilograms per cubic meter. As long as you're measuring an amount per unit of volume, then you're measuring concentration. But the standard is moles per decimeter cubed. Now, a quick note about interconversion between these units before we go any further, because this is something that trips up some students occasionally. So here's a question for you. If I wanted to convert, so any measure of volume, when we measure a length, we measure it in units of length, and the standard units of length would be meters. If we're measuring an area, we would multiply one dimension by the perpendicular dimension. So we would multiply this width by this height here. But if we're measuring a volume, we are measuring three dimensions which we're multiplying by each other. So a volume would be measured by multiplying this length by this length by this length here. So let's imagine that we have each of these sides of a cube, let's call, well, they're all going to be the same length, x. So let's say x is 1 centimeter. Then the volume of this cube is going to be 1 times 1 times 1. But each one of these 1 centimeter measures is measured in centimeters. And so the units that we're going to be measuring this volume in will be in cubic centimeters. If we were measuring this in meters, it would be the same thing. It would be 1 by 1 by 1 meters, and the units would be meters cubed. But a decimeter cubed, 1 decimeter, the term decimeter on its own, this means 1/10 of a meter. So a decimeter cubed, if 1/10 of a meter is 10 centimeters, so in this case a decimeter cubed, or I should say a cubic decimeter, would imply that this cube, the volume of this cube that we're measuring, the sides of the cube are each 10 centimeters, 1/10 of a meter. And so what we have here is 10 centimeters by 10 centimeters by 10 centimeters. So 10 by 10 by 10 gives 1,000, and because we're multiplying centimeters by centimeters by centimeters, the units are going to be centimeters cubed. So a cubic decimeter, which we write as dm cubed, is equivalent to 1,000 centimeters cubed. Now, many of you will know that 1,000 centimeters cubed is what we mean when we say 1 liter. So 1 liter is 1,000 centimeters cubed, and a cubic decimeter is the same thing. So decimeters cubed is the same as liters, essentially. So just be aware of these things. And one final point here. If I wanted to find out, so here's a question for you guys to answer. I'm going to ask this and then pause the video. Well, I'm going to pause and let you guys answer this. Again, if you're watching as a recording, the video will pause and the question will pop up. So how many cubic centimeters are there in a cubic meter? So if you have a cube with sides of 1 meter in length, how many centimeters cubed are there in that cubic meter? Okay, so here's how you do this. So if you have sides of 1 meter in length, and you want to find out what the volume is in centimeters cubed, then you have to be aware that 1 meter is 100 centimeters. So if this side of the cube is 100 centimeters, and this side of the cube is also 100 centimeters, and this side of the cube is also 100 centimeters, then the volume of this cube in cubic centimeters is 100 times 100 times 100, which gives you 1 million cubic centimeters. So 1 cubic meter contains 1 million cubic centimeters. So what that also means is if 1 liter or 1 decimeter cubed is 1,000 centimeters cubed, then a cubic meter contains 1,000 cubic decimeters. So these are just ways that you need to be aware of to interconvert between these different volumes, different units of volume. And occasionally exam questions may try and throw you off by including a unit conversion somewhere in the exam question. Now, the way to think about it when you're dealing with converting volumes is just be aware of this idea of the volume of a cube being the sides multiplied by each other, and that the units are also multiplied by each other, and how to convert between the units like I've just shown here. Okay, so let's go on to talk a little bit more about concentration, and then we'll go through some basic examples, and then towards the end of the lesson, as I say, I'm going to go through 7 exam questions, which are a little bit more challenging, but should illustrate the kind of typical ways in which you would solve these types of problems. So 1 decimeter cubed of a solution, let's say 1 decimeter cubed of a solution of water 1 decimeter cubed of water contained 117 grams of sodium chloride to make a sodium chloride solution. So how would we calculate the concentration of this solution? Well, we could calculate it in grams per decimeter cubed, or we could calculate it in moles per decimeter cubed. If we wanted to give it in grams per decimeter cubed, then sodium chloride is the solute. So it would be 117 grams per cubic decimeter, and that would be it. But if we wanted to calculate it in the more standard measure, which is moles per decimeter cubed, we would first need to calculate the number of moles of sodium chloride that we have. Now, as we saw before, in order to do that, you need to know what the relative formula mass of sodium chloride is. And from the periodic table, the relative formula mass is 23 for the sodium and 35.5 for the chlorine, which gives us a relative formula mass of sodium chloride of 58.5. So if we have 117 grams of sodium chloride and its relative formula mass is 58.5, then to calculate the number of moles that we have, we need to divide 117 by 58.5, and this tells us what the concentration of the solution is in moles per decimeter cubed. So when we do this, we find that the concentration of the solution is 2 moles per decimeter cubed. So let's have a look at another example here, and I'm going to pause here and let you guys try this one for yourself. So how many grams of copper sulfate are present in 500 centimeters cubed of a 1 mole per decimeter cubed solution of copper sulfate? Now, to make things a bit easier, I'm going to give you the relative formula mass of copper sulfate here. So what do you guys think? All right, so let's see how this one is done. So here, what we need to do is to perform a calculation that looks a bit like this. So we have the relative formula mass, and we have the volume of a solution, and we have the concentration of the solution. So if we know that there is 1 mole in every decimeter cubed, but the actual volume of solution that we have is 500 cubic centimeters, then we can simply multiply the relative formula mass by the solution concentration and then multiply that by the volume that we have in cubic decimeters. So the mass is going to be 79.75 grams. And that gives us 79.8 grams to 3 significant figures here. Now, before we go any further then, let's just take a look at a couple of very important mathematical relationships, one of which we mentioned in the previous lesson where we talked about the concept of the mole, and another one is specific to concentrations, and it goes to what we're saying here. Now remember, whenever you have an equation, it should be translatable into a verbal statement. And conversely, when you have a verbal statement which describes the definition of a quantity, such as concentration, like this one, you should be able to translate it directly into an equation. So the equation that we saw which defined what we mean by a mole is the number of moles, N, is equal to the mass of a substance in grams, lowercase m, divided by the relative mass of that substance, uppercase M. So this is the first of the 2 very important equations that I want all of you to memorize. So, and again, if you need to rearrange this equation and you have trouble with the algebra and you need one of these formula triangles, you can rearrange it like this. Now, the other equation is the one which is again a mathematical translation of this statement here. So the concentration of a solution is the number of moles, concentration C in moles per decimeter cubed, is the number of moles of the solute dissolved in the solvent divided by the total volume of solution that you have. So this would be the other very important equation here. And this relates specifically to solutions. And again, if you need a formula triangle to rearrange this equation, you could have it like this. So this one relates to solutions specifically. And remember that the number of moles here is of the solute. And the V here is the total volume of the solution. Now, when you enter these values here, number of moles of solute and total volume of the solution, typically you're going to be entering the total volume of solution in cubic decimeters. That is the more standard way of doing it. Number of moles of solute is just a number of moles. It doesn't have units. And the concentration will therefore always be in moles per cubic decimeter. Now, sometimes students get a bit confused because they may not see the concentration being the units of concentration being given like this. They might see it given like this: moles times decimeters to power minus 3. But these two are equivalent to each other. When you divide something which is raised to the power of something, it's the same as multiplying by that thing raised to the negative power, the same negative power. So these two are equivalent to each other. These are both units of concentration. Now sometimes this is abbreviated to capital M, which is the symbol, the unit of molarity. So if you see, for example, an exam question which says you have a 0.5 capital M solution of, let's say, sodium chloride, then what it's talking about is a 0.5 moles per cubic decimeter solution of sodium chloride. So when you see this, it just means molarity, which is another way of saying concentration. It's a shorthand way of saying concentration. Now, to illustrate to you, before we go any further, what exactly concentration means a little bit more visually, I'm going to use a couple of these animations or simulations that you can find on the PHET website. So this one is entitled Concentration, and it basically shows you what we mean by concentration. Here you have a volume of liquid, and you can use a drink mix, which is kind of a bit wishy-washy. I prefer to use an actual solution. These are all substances which, when you dissolve them in water, they give colored solutions. So the more concentrated the solution becomes, the more intense that color becomes. So let's take a look at nickel 2 chloride. So if I have a half liter, which again is the same as 500 milliliters or 500 cubic centimeters. Remember, 1 liter is the same as 1 cubic decimeter. If I put some nickel chloride into here, we can see that the concentration increases because I'm adding more solute into the same volume of solution. If I now add more solvent, more water, we'll see that the concentration decreases because we have the same number of moles of nickel chloride particles, but we now have a greater volume of solution. We're dividing the same number of moles by a larger volume, and so the concentration decreases. If I decrease the amount of solution, if I now pour off the solution, we can see that the concentration remains the same. The volume of the solution is decreasing because I'm losing the solvent and the solute. Now, if I evaporate this solution, we can see here that as the solution evaporates, we're not losing the nickel chloride, we're losing the water. And so as the solution evaporates, the concentration increases until eventually you're just going to be left with nickel chloride crystals here. So this simulation kind of gives you a sense of what we mean by concentration. Now there's another simulation which is entitled molarity, which is similar. It gives you again a sense of what we mean by molarity. Now every different kind of solute will have a point beyond which you can't dissolve anymore in a given volume of solvent. So the way that I like to think about this is, if you imagine you're making a cup of tea or coffee and you're pouring in lots and lots of sugar while stirring it. Well, at first the sugar will dissolve in the coffee or in the tea, but eventually you will have added so much sugar that it will stop dissolving. You're essentially just going to see sugar crystals sitting at the bottom of the volume of coffee or tea. And so this is what we call a saturated solution. A certain volume of solvent will only hold a maximum amount of solute. If you add more than that, the solute will no longer dissolve, it will come out of solution. So you can see this on this diagram. So again, I'm going to use nickel 2 chloride. So what we have here is, let's say if we put a liter of nickel 2 chloride. If I increase the amount of solute, here we can see the amount of moles being added. So at the moment we have 0.5 moles of nickel chloride dissolved in 1 liter or 1 cubic decimeter of water. If I increase the amount of nickel chloride that we add, we see that the concentration rises accordingly. Now, if I decrease the volume of the solvent by evaporating it, for example, you can see here that the concentration rises because we still have the same number of nickel chloride, the number of nickel chloride particles dissolved, but we now have them dissolved in a smaller volume. And so now the concentration rises. Now, if I now change this to another solution here, so let's say potassium permanganate. Now, if I decrease this, so let's say we start with 0.26 moles of potassium permanganate or potassium manganate 7 dissolved in 0.662 litres. This is 662 cubic centimetres or 0.662 decimeters cubed of water. If I now dissolve more and more potassium permanganate, eventually we will reach a point where the water cannot dissolve any more potassium permanganate, and any further crystals of the solid that I add will simply stay as solid crystals in that saturated solution. So this is what we mean by molarity. You can see here that the concentration, solution concentration, is given that prefix, or rather that unit, M, capital M for molarity, and this stands for moles per cubic decimeter. So, for example, if I go back to our nickel 2 chloride, we have 1 mole in 1 cubic decimeter here. So 0.5 moles of the solid dissolved in 0.5 liters of the solvent. So 0.5 moles of the nickel chloride is dissolved in 0.5 decimeters cubed of the water, and this gives us a concentration of 1 mole per decimeter cubed. If I raise this to 1 and raise that to 1, we still have 1 mole per cubic decimeter. And this shows you that the molarity is another way of describing the number of moles of solute that you have dissolved per cubic decimeter. So again, I'm going to embed these on the this lesson's page. We're going to be coming back to the concept of molarity and concentration in a later lesson on chemical analysis, where we talk about titrations. Now, I'm going to be, towards the end of this lesson, looking at a couple of titration type calculations briefly, but there will be a whole lesson on titrations, including the practical elements of doing a titration later on in the course. And so we're going to be revisiting this concept, but I will embed both of these simulations on this lesson's page on the GCSE chemistry course, just so you guys can kind of play around with them without necessarily having to find the pages on the PHET website there. So we'll come back to the idea of concentration a little bit later on in this lesson. Let's take a look back now at a really important concept of the mole in terms of the number of particles. Now remember from the last lesson, 1 mole of particles is Avogadro's number of particles. So this was named after Amedeo Avogadro, and the number is 6.02 to 2 decimal places, 6.02 times 10 to the power 23. This is the number of particles in 1 mole of any substance. So, to give an example, 2 grams of hydrogen gas contains this many molecules of hydrogen. So hydrogen gas has the formula H2, and so as we said before, 1 mole of any substance will have a mass in grams numerically equal to its relative mass. Now, since the relative atomic mass of hydrogen is 1, and we have 2 atoms of hydrogen in every molecule of hydrogen gas, then the relative mass of this particle, this molecule, is 2. And so if you have 1 mole of these particles, if you have 6.02 times 10 to the power 23 hydrogen molecules, you will have a total mass in grams of 2 grams. So another example that we saw before is that the relative atomic mass of helium is 4. So if we're dealing with 1 mole of individual helium atoms, this would have a mass of 4 grams. So 4 grams of helium contains Avogadro's number of atoms. Another example that we saw before is that the relative atomic mass of oxygen is 16. Therefore, 1 mole of individual oxygen atoms will have a mass of 16 grams. But we know that oxygen gas is composed of molecules, each of which contains 2 atoms of oxygen. And so 1 mole of oxygen molecules is going to have a mass of 32 grams. So this gives us, again, a sense of what we mean by 1 mole and the significance of the concept of the mole. And this is encapsulated within that first equation. If 1 mole of any substance has a mass numerically equal to its relative mass, then this is why we see this equation in this form. The mass in grams divided by the relative mass gives you the number of moles. So if you have 1 mole, these 2 numbers must be the same. So another example, water. So what the relative formula mass of water is 18, and so 1 mole of water molecules would therefore have a mass of 18 grams. But 18 grams of water contains 1 mole So we would have 6.02 times 10 to the power 23 molecules of water in 18 grams of water. Now, another of Avogadro's contributions to our understanding of chemistry is stated as Avogadro's law, and this concerns gases. And it basically states that equal volumes of different gases, which are at the same temperature and pressure, will always contain the same numbers of particles. So this means that for the reaction between hydrogen gas and chlorine gas to make hydrogen chloride, so you can visualize this in terms of the numbers of particles. Again, if we have one molecule of hydrogen reacting with one molecule of chlorine gas, each of these are diatomic molecules, and so they're represented by these two pictures here. We're going to form two molecules of hydrogen chloride gas, and so we would have two of these. Now, if we had 1 decimeter cubed of hydrogen and 1 decimeter cubed of chlorine gas, we're going to form 2 decimeters cubed of hydrogen chloride gas. And this all goes down to the idea that gases at the same temperature and pressure, if they have equal volumes, they will contain equal numbers of particles. So this means, another example, this means that the reaction between hydrogen gas and nitrogen gas to make ammonia, we could visualize like this. 3 molecules of hydrogen react with 1 molecule of nitrogen to make 2 molecules of ammonia. Therefore, if you, for example, had 300 cubic centimeters of hydrogen gas and 100 cubic centimeters of nitrogen gas, you're going to make 200 centimeters cubed of ammonia. Now this ignores the reversible nature of this reaction. We're going to be looking at the reversible reactions in a later lesson. This type of reaction, this reaction between hydrogen and nitrogen, is in fact a reversible reaction. But we're just concerned here with the reaction going in this direction, forming ammonia from its elements, hydrogen and nitrogen. So we've been talking about concentrations and we've been talking about gases. We're going to come back to those a little bit later on, but now let's take a look at how we would go about calculating masses of reactants and products in a very basic way that we've already seen, and then later on we're going to be looking at some more kind of typical examples that you might find in exam questions. So if we imagine that 10 grams of sodium chloride is produced when sodium is burned in excess chlorine or reacts with excess chlorine, what would be the mass of sodium that was used to form this 10 grams of sodium chloride? So here we have the relative atomic masses of sodium and chlorine. So I'm going to pause here and let you guys have a go at this question for yourselves. So what do you think? What mass of sodium would be required in this reaction to form 10 grams of sodium chloride? All right, so let's see how we can approach this. Now, there's a couple of different ways you can go about doing this. And a bit later on, I'm going to kind of give you a general method of solving problems where you're trying to calculate the amounts of reactants or products involved in a chemical reaction, whether they are solids or liquids or gases or solutions. There is a kind of general approach that you can take. But I'm going to kind of simplify it a little bit for these first couple of examples. So whenever you're solving a problem like this, you have to start with the balanced symbol equation. That is always your starting point because it gives you the relative numbers of moles of particles of your reactants and your products. So in this case, the balanced symbol equation is one that we've seen before. 2 sodium atoms will react with 1 chlorine molecule to make 2 formula units of sodium chloride. And so if we consider the masses involved in this, if we had 2 lots of, let's say 2 moles of sodium, we would have 2 times the relative mass of sodium, which is 2 times 23, which gives 46 grams of sodium. The relative formula mass of chlorine here, or the relative mass of a chlorine molecule, is going to be 2 times 35.5. And so if we're trying to work out just the sodium, we don't really need to consider the chlorine. We just need to consider the ratio between the sodium and the sodium chloride. So we see here that the ratio of moles in the equation is 2 moles of this will react to give 2 moles of this. So we can say that we're going to form 117 grams of sodium chloride when we use 46 grams of sodium. And so we can now, from these two numbers, we can work out if we had 1 gram of, if we're producing 1 gram of sodium chloride, we're going to require 46 divided by 117 grams of sodium. So this gives us the amount of sodium required to produce 1 gram of sodium chloride. Therefore, if we're trying to produce 10 grams of sodium chloride, we would simply multiply this value by 10, and this tells us that the answer is 3.9 grams of sodium. So let's try another example here. If 5 grams of magnesium oxide is produced when magnesium is burned in excess oxygen, what mass of magnesium would be used to produce 5 grams of magnesium oxide? So again, I'm going to pause here and let you guys have a go at this question for yourselves, see what you can come up with. Okay, so here's how we do this. Again, we have to start with the balance symbol equation. Again, it's one that we've seen before. So in this case, if we imagine that we had 2 moles of magnesium, this would give us a total mass of 48 grams of magnesium. And because the ratio of moles is 1 to 1 here, we would produce 2 moles of magnesium oxide. And so this would give us 2 times the relative formula mass of magnesium oxide in grams, which is 80 grams of magnesium oxide. Now again, so we can see here from these numbers that when we use 48 grams of magnesium, we produce 80 grams of magnesium oxide. Therefore, if we wanted to produce 1 gram of magnesium oxide, we would divide 48 by 80, and this tells us that it requires 0.6 grams of magnesium. Therefore, if we're trying to produce 5 grams of magnesium oxide, we would multiply this value by 5 to get 3 grams of magnesium as the answer. So here's another one. And again, I'm going to pause here and let you guys have a go at this for yourselves. So if 10 grams of calcium chloride is produced when calcium carbonate is reacted with excess hydrochloric acid, what mass of calcium carbonate was used? So again, here are the relative formula mass values. I'm going to pause here and let you guys have a go at this one. Okay, so here's how we do this one. Again, we start with the balance symbol equation. So when an acid reacts with a carbonate, we always get a salt and carbon dioxide and water. So in this case, if we had 100 grams of calcium carbonate, which is 1 mole of calcium carbonate, the relative formula mass is 100. So 1 mole of calcium carbonate is going to have a mass of 100 grams. So the ratio of moles here between calcium carbonate and calcium chloride is 1 to 1 here, because neither of them have a whole number in front of them. This means that you have 1 mole of this will produce 1 mole of this. So if the ratio is 1 to 1, we would expect to produce 1 mole of calcium chloride, and therefore in grams that would be the relative formula mass of calcium chloride. So that's 111 grams. So we can see here that 111 grams of calcium chloride is produced when 100 grams of calcium carbonate reacts with excess acid. In other words, enough acid to make sure that you've completely reacted all of the calcium carbonate. Therefore, if we wanted to produce 1 gram of calcium chloride, we would divide 100 grams by 111, and this tells us that we require 0.9 grams of calcium carbonate to produce 1 gram of calcium chloride. So now we can answer the question. To produce 10 grams of calcium chloride, we would need to multiply this value by 10, and this of course gives us 9 grams of calcium carbonate required. So this is a very simple approach to calculating the mass of a reactant required to produce a specific mass of product. But what about if you wanted to calculate what mass of product you could expect to produce if you have a specific mass of reactant? So again, I'm going to show you a basic method here, which is a very similar approach, and it goes down to, again, identifying the balance symbol equation, getting the molar ratio of the substances that you're considering, and then doing the calculation. So here's one to try for yourself. What mass of magnesium oxide is produced when 30 grams of magnesium is burned in excess oxygen? So here we have the relative atomic mass values for magnesium and oxygen. So again, I'm going to pause and let you guys have a go at this one for yourselves. All right, so again, the approach that we take here is very similar. We start with the balance symbol equation, and then we calculate the masses in terms of the moles of each substance in the actual balance symbol equation. So here we can see 2 moles of magnesium react to produce 2 moles of magnesium oxide. So imagine that we had 2 moles of magnesium. Well, 2 moles of magnesium will have a mass in grams numerically equal to 2 times the relative mass of magnesium. So this is 48 grams of magnesium, and this is going to produce 80 grams of magnesium oxide. The relative formula mass of magnesium oxide is 24 for the magnesium plus 16 for the oxygen, but we're making 2 moles of it, so we would have double that. So we see here that 48 grams of magnesium produces 80 grams of magnesium oxide. So what this means then is that 1 gram of magnesium will react to produce 1.667 grams of magnesium oxide. Therefore, if we had 30 grams of magnesium, we would expect to produce 30 times this amount of magnesium oxide, which is 50 grams of magnesium oxide. Let's try another one here. So, when you're calculating the mass of products, remember that the relative formula mass of a compound is the sum of all of the relative atomic masses of all the atoms in that compound added together. So what mass of sodium chloride is produced when 25 grams of sodium is burned in excess chlorine? So again, I'm going to pause here and let you guys have a go at this one. You have the relative atomic mass values of sodium and chlorine here. Have a go at this one and see what you can come up with. Okay, so again, we start with the balance symbol equation. And so from the balance symbol equation, we can see that 2 moles of sodium react to produce 2 moles of sodium chloride. Now, each mole of sodium will have a mass in grams numerically equal to the relative atomic mass of sodium. So 2 moles of sodium will have a mass of 46 grams. The relative formula mass of sodium chloride is 23 for the sodium plus 35.5 for the chlorine. We're producing 2 moles of it, so it would be 2 times that in grams, which is 117 grams. So we see here from these numbers that 46 grams of sodium reacts to produce 117 grams of sodium chloride. Therefore, 1 gram of sodium is going to react to produce 117 divided by 46, which is 2.54 grams of sodium chloride. So if you started with 25 grams of sodium, and we're assuming that you've reacted all of it because you're burning it in excess chlorine, you're going to produce 25 times this number of grams of sodium chloride, which is 63.5 grams of sodium chloride. Let's try one more example before we move on. So, what mass of calcium chloride is produced when 10 grams of calcium carbonate is reacted with excess hydrochloric acid? So once again, here are the relative atomic mass values of these elements. Have a go at this one. Okay, so we start with the balance symbol equation. And so from here, we can see that in terms of the substances we're interested in, calcium carbonate and calcium chloride, the ratio of moles is 1:1. So 1 mole of calcium carbonate is going to have a mass of 100 grams, which is the relative formula mass of calcium carbonate, and 1 mole of calcium chloride is going to have a relative mass, 1 mole of calcium chloride is going to have a mass in grams of 111 grams, which is the same numerically as the relative formula mass of calcium chloride. So we see here from these numbers that if we had 100 grams of calcium carbonate, we'd expect to produce 111 grams of calcium chloride. Therefore, 1 gram of calcium carbonate is going to react to produce 1.11 grams of calcium chloride. So if we go back to the question, it's asking when we have 10 grams of calcium carbonate, how much calcium chloride could we expect to produce? Well, we would multiply this number by 10, and this gives us 11.1 grams of calcium chloride. So let's go back to solutions now before we finish off with some gas volumes and some exam questions. So if you had to determine what mass of solute is present in a solution, there's a couple of ways you could do this. So imagine you were asked how much copper sulfate is present in 1 cubic decimeter of a solution. Now this depends on the concentration, obviously. Now the relative formula mass of copper sulfate is 1.595 grams. 1.595, that's the relative formula mass of copper sulfate. So let's imagine we had 10 cubic centimeters of a solution, which when evaporated, like this, so if you imagine you have your copper sulfate here in a watch glass, you put it onto the top of a beaker, and then you heat the beaker from below, and the steam will gently heat the bottom of the watch glass, which would evaporate the solvent from this solution of copper sulfate. Eventually, what you would be left with is copper sulfate crystals here. So, the original solution, if we look at these numbers, the original solution must have contained 0.5 multiplied by 1,000 divided by 10 grams of copper sulfate crystals. So this gives us 50 grams. So we see here that the concentration in terms of grams per cubic decimeter of the original solution is 50 grams per cubic decimeter. So let's take a look at another example. So when evaporated, 5 cubic centimeters of solution produces 0.1 grams of copper sulfate crystals. So what was the original concentration in grams per cubic decimeter of the original solution? Again, I'm going to pause here and let you guys have a go at this one for yourselves. Okay, so here's how you do this one. So in this case, we have 0.1 grams, and then we multiply that by 1,000 over 5, which gives us 20 grams. So the original solution has a concentration in grams per cubic decimeter of 20 grams per cubic decimeter. So back to gas volumes then. So 1 mole of any gas at room temperature and pressure, or RTP, has the same volume, which is 24 cubic decimeters, which is the same again as 24,000 cubic centimeters. Now this relationship can be it can be expressed like this, and if you need to rearrange this equation and you need one of these formula triangles, then you can use this one. So the gas volume is equal to moles multiplied by the molar volume, which is 24 cubic decimeters at room temperature and pressure. At standard temperature and pressure, it's a different volume, but here we're talking about room temperature and pressure here. So if you wanted to rearrange this equation to find the number of moles of gas that you have, you would divide both sides by the molar volume. And if you wanted to rearrange the equation to calculate the molar volume, you would divide both sides by the number of moles. So here's one for you guys to try. So calculate the volume at room temperature and pressure of 16 grams of helium gas. So again, the relative atomic mass of helium is 4. Have a go at this one for yourselves. All right, so here's how you do it. So in this case, we need to calculate, we've got the mass, but we don't have the number of moles. So we're trying to calculate the gas volume, and we know what the molar volume at room temperature and pressure is. It's 24 cubic decimeters. So the first step is to calculate the number of moles. So we know the relative atomic mass of helium. We know that helium, being a noble gas, will be composed of individual unbonded atoms. So the number of moles is simply going to be the mass in grams divided by the relative mass, which is 4. So now we can substitute 16 divided by 4 into this equation here, where we have gas volume is the number of moles times the molar volume. So we have the volume is 16 over 4 times 24, which gives us 96 cubic decimeters. Here's one more example. So calculate the mass at room temperature and pressure of 72 cubic decimeters of hydrogen gas. So the relative atomic mass of hydrogen is 1. The relative formula mass, remember, of hydrogen gas, because it's a diatomic gas, is 2. So how would you do this one? Have a go at this one for yourselves. Okay, so remember that mass is equal to moles multiplied by relative mass, and this goes back to the equation that essentially defines the mole. Number of moles is equal to the mass in grams divided by the relative mass. When we rearrange this equation to make mass the subject, mass is going to be equal to the number of moles multiplied by the relative mass. So we have this expression, and therefore we can, once we've, and we also have the expression for the number of moles for a gas, which is this. So we can write these first two expressions here. So from the information that we're given, we know the molar gas volume at room temperature and pressure is 24. So to calculate the number of moles of hydrogen gas that we have, if we have 72 cubic decimeters at room temperature and pressure, we would divide the volume of gas that we have, which is 72, by the molar volume, which is 24. So this gives us 3 moles of hydrogen gas. Now we can calculate the mass that we have, because we know that the mass is going to be equal to the number of moles that we have multiplied by the relative mass of the substance, in this case the relative mass of hydrogen gas, which is 2. So the mass is going to be 3 times 2, which gives us 6 grams. Okay, so now I'm going to go through a number of exam questions which some of the students that I have in attendance with me requested that I go through. Now you actually requested quite a few of the exam questions that you all received in your homeworks. These are some of the ones that were most widely requested for me to go through. Some of the other questions that you guys have asked both prior to this lesson and in the Q&A box of the Zoom client that I can see during this lesson go a little bit beyond the scope of GCSE chemistry. I will answer those in the Q&A session that will follow the recorded segment of this lesson. But for now, I'm just going to go through these 7 exam questions here because I feel like they're very useful questions to illustrate some of the principles that we've been talking about in slightly more challenging exam style questions. So here's the first one. So what mass of carbon monoxide is needed to reduce 1 kilogram of iron oxide to iron? So here we have this first problem here. Go ahead and have a go at this one for yourselves. All right, so let's walk through how we do this problem. So first of all, you'll notice that the mass that we've been given is of the iron oxide that we're starting with is not in grams, it's in kilograms. So the first thing that we need to do is to convert this mass into grams. So this is 1,000 grams. So now this goes to what I was saying before. There is a general approach that you guys can take to solving problems concerning calculations of reactants and products. And it doesn't really matter whether you're dealing with a calculation involving masses or solutions and concentrations or volumes of gases. The general approach is always the same. Your first starting point is the balanced symbol equation. Now, the balanced symbol equation has been given to you in this exam question, but if you don't have it, then you can work it out for yourself from first principles. But here in this case, we have the balanced symbol equation. Now, the reason for this is this gives you the molar ratio. So the molar ratio is the ratio of the numbers of the particles that you're concerned with in the question. In this case, we're trying to work out the mass of carbon monoxide, which is needed to react with this mass, 1,000 grams of iron oxide. So these two are the substances in question, and the molar ratio is 1 to 3. So this is your first step in solving any calculation problem. Your second step is to calculate the number of moles of any reactant or product. So you look at the information that you've been given and you make sure that before you go any further, you use the available information to calculate the number of moles of any of the reactants and products in the equation. It doesn't matter which one. As long as you can calculate the number of moles of any of these, you can go on to the next step. Now, in this case, we've been given the mass of iron oxide. So we have mass is 1,000 grams here. To calculate the number of moles of this, we would need the relative formula mass of iron oxide, because remember, number of moles is equal to the mass in grams divided by the relative mass of a substance. So because this is an exam question, this comes from essentially a context where you would have a periodic table available to you. If you look up the relative atomic mass of iron, it's 56. Relative atomic mass of oxygen is 16. I'm rounding to the nearest whole numbers here. And so the relative formula mass of iron oxide is going to be 56 times 2 for the 2 iron atoms, and we add this to 3 times 16 for the 3 oxygen atoms. So this gives us a total relative formula mass of 160. So we have the relative formula mass, we have the mass, we can now calculate the number of moles and take care of this second step. So the number of moles is going to be the mass, 1,000 grams, divided by the relative formula mass, which is 160, and this gives us 6.25 moles. So we're starting with 6.25 moles of iron oxide. Now the next step is to apply the molar ratio to work out the number of moles of the substance in question. So in this case, the substance we're being asked to calculate the amount of is carbon monoxide. We're being asked to calculate the mass of it, but in this step we're going to calculate the number of moles, and we simply apply the molar ratio. So we see here that for every 1 mole of iron oxide, we're going to need 3 moles of carbon monoxide. So the molar ratio is 1 to 3, therefore the number of moles of carbon monoxide is going to be 3 times the number of moles of iron oxide that we had. So this is going to be 6.25 times 3, which gives us 18.75 moles of carbon monoxide. Now the final step, if required, if you're being asked to calculate the number of moles of something, you would stop here, but we're being asked to calculate the mass. So the final step is use the number of moles and the appropriate equation to find the answer. Now, by appropriate equation, it depends on what you're being asked to calculate. In this case, we're being asked to calculate a mass. So the appropriate equation would be this one: N is equal to mass in grams divided by the relative mass. If you're being asked to calculate, say, a concentration or a volume of a solution, you would use this one. If you're being asked to calculate a gas volume, for example, you would use this one here. Moles is equal to gas volume divided by molar volume. But depending on what the exam question is asking you, you would use one of these 3 relationships. So this would be the gas volume divided by the molar volume. So whichever of these equations is appropriate to the question, now that you have the number of moles of the substance you're being asked about, you can then calculate whatever the equation is asking you to calculate. So in this case, we're being asked to calculate the mass of carbon monoxide. Now the relative formula mass of carbon monoxide is going to be 12 for the carbon plus 16 for the oxygen. So this would give us 28. And so if the mass is going to be equal to the number of moles, mass of carbon monoxide is equal to the number of moles of carbon monoxide multiplied by its relative mass. So this is going to be 18.75 times 28, which gives us a mass of 525 grams. So this is the general approach, and as you'll see, pretty much regardless of the question that you're being asked to solve, with a few tweaks here and there, this is the general approach that we're going to take to solving these questions. So that's the first one. Here's the second one. So what mass of sulfur trioxide is formed from 96 grams of sulfur dioxide? Again, we're being given the balance symbol equation here. So again, I'm going to give the students in attendance with me who didn't answer this question correctly in their homework a chance to have a go at this. Again, if you're watching this on my website, the video will pause, the question will pop up, and you'll be able to answer it interactively. If you're watching it elsewhere, maybe pause the video, get a pen and paper out and a calculator, see if you can work this out for yourself, and you will need a periodic table as well. All right, so this is how we would approach this. Again, we have the balance symbol equation. So step 1 gives us our molar ratio. So the 2 substances we're being asked about is sulfur trioxide, which is SO3, and sulfur dioxide, which is SO2. So we can see here that the molar ratio is 2 to 2, or 1 to 1 of these substances. So that's our starting point. Our second step is to calculate whichever one of these we have sufficient information for, to calculate the number of moles of one of these substances. So we're being told the mass of sulfur dioxide that we're starting with. So we have a mass of 96 grams of sulfur dioxide, and if we know the relative formula mass of sulfur dioxide, we can work out the relative or the number of moles of sulfur dioxide and take care of the second step. So the relative atomic mass of sulfur to the nearest whole number is 32. Relative atomic mass of, so this is the relative atomic mass of sulfur. Relative atomic mass of oxygen is 16, and we have 2 oxygen atoms and 1 sulfur atom. So the relative formula mass of this is going to be 32 plus 2 times 16, which gives us 64. So the relative formula mass of sulfur dioxide is 64. So now we can take care of this second step, which is to calculate the number of moles of one of these substances, in this case SO2. So the number of moles of sulfur dioxide is going to be the mass in grams divided by the relative mass, 64, which gives us 1.5. 1.5 moles. So that's step 2. Now step 3, if we look at the molar ratio between the substance that we've just calculated the number of moles we have of and the other substance, the substance in question, which is SO3, we see that the ratio is 1 to 1. So if we have 1.5 moles of this, we must produce the same number of moles of sulfur trioxide. So number of moles of SO3 is going to be 1.5 moles because of the molar ratio of 1 to 1. So now we can go ahead and solve the question, because we're being asked not the number of moles of sulfur trioxide, but the mass of sulfur trioxide. So in this case, we need the equation number of moles is equal to mass divided by relative mass. The relative mass of sulfur trioxide here is going to be 32, so this is the relative formula mass, 32 for the sulfur plus 3 times 16 for the 3 oxygens. So this gives us a relative formula mass of 80 for sulfur trioxide. So the mass, if we rearrange this equation, the mass of sulfur trioxide is going to be the number of moles of sulfur trioxide multiplied by its relative formula mass. So we have 1.5 times the relative formula mass, which is 80, which gives us 120 grams of sulfur trioxide. So let's have a look at the third question here. Now this one caused a few headaches for some of you. Now this is perhaps a little bit more of a challenging question. 4.17 grams of hydrated barium bromide crystals. So here we see the formula of hydrated barium bromide. Barium bromide and then this dot and then NH2O. Now this is an expression which describes not just the formula of barium bromide, but what we call the water of crystallization. Now many ionic compounds, such as barium bromide, in their hydrated form, they have absorbed water molecules, and for every formula unit of the ionic compound, in this case barium bromide, there is a certain number of molecules of water associated with each formula unit. So N here is being used because we're trying to calculate how many moles of water molecules are associated with each mole of barium bromide. So this expression with the dot, it basically says that for every 1 mole of barium bromide particles, there are N moles of water molecules associated with them. So we have 4.17 grams of these hydrated barium bromide crystals. Now, this gives 3.72 grams of anhydrous barium bromide. Anhydrous means with no water of crystallization. So anhydrous barium bromide just has the formula of barium bromide, BaBr2. It has no water molecules associated with it. But by doing this, by heating this to constant mass, what this means is you take your hydrated crystals, you heat them, and as you're heating them, the water of crystallization is driven off the crystals until eventually you just have the dry anhydrous crystals. And at that point, the mass of the crystals will not change, even under heating. So on heating to constant mass, this 4.17 grams of hydrated barium bromide crystals gave 3.72 grams of anhydrous barium bromide. So work out the relative molecular mass of the hydrated barium bromide and the value of N. So again, this one was a little bit more challenging for some of you. So again, I'm going to give you guys a chance to have a go at this for yourselves, and then we'll go through the solution. And again, if you're watching this as a recording, I'd encourage you to either pause the video and try this for yourself, or if you're watching this on my website, the video will pause and the question will pop up now. Okay, so for this, again, you would need to use the periodic table, first of all, to identify the relative atomic masses of barium and bromine, and hopefully by now you know the ones for hydrogen and oxygen. Now I'm going to use these ones. So relative atomic mass of barium is 137.3. The relative atomic mass of bromine is 79.9. So the relative formula mass of barium bromide, anhydrous barium bromide here, is going to be 137.3 plus 2 times 79.9 for the two bromine atoms in this formula. And so this gives us a relative formula mass for anhydrous barium bromide of 297.1. Oh, 200, let me just rub that out. 297.1. Now, it doesn't really matter if you maybe round it up to 80 for this one and 137 for this one. As we'll see, it won't make any difference. I'm just using the slightly more precise values here. So that's the relative formula mass of barium bromide when it's anhydrous. Now, we don't know the relative formula mass of this because we don't know how many molecules of water are involved in it. We first need to work out what N is. Now, we know that the relative formula mass of water is 18. It's 2 for the two hydrogens plus 16 for the oxygen. So this is going to be 18. So let's start with our step 1 here. Step 1, we have the balance symbol equation, and we see here that the ratio of moles of barium bromide to water is 1 to N. So this is going to come in handy in a little while. So let's take a look at what the question is actually telling us here and see what we can work out from the question. So we started with 4.17 grams of this. We ended with 3.72 grams of this. So the number of grams of water that must have been driven off is the difference between these two values. Remember, mass is conserved in a chemical change. So if you're starting with a certain amount of mass, and in this case we only have one reactant, you're going to end with the same total amount of mass. So if the total amount of mass on the right-hand side must be equal to the total amount of mass on the left-hand side of the equation, then we can work out what the mass of water was. So the mass of water is going to be 4.17 minus 3.72. So this gives us a mass of water of 0.45 grams. Now what this tells us is that 0.45 grams of water was driven off the hydrated barium bromide crystals. But that must mean that however many moles of water that this is must have been the water of crystallization for the original anhydrous barium bromide. So we know that the mass of water is this. We know the mass of barium bromide here that's produced, the anhydrous barium bromide, is 3.72. So we can go ahead to the second step here and calculate the number of moles of barium bromide. Number of moles of anhydrous barium bromide. So this is going to be the mass, 3.72 grams, divided by the relative formula mass of this, which was 297.1 grams. So this gives us 0.0125 moles of barium bromide. Now we also have the mass of water here, and we have the relative formula mass of water, so we can also work out the number of moles of water that we have. So number of moles of H2O is equal to the mass, which is 0.45, divided by the relative mass, which is 18. So the number of moles of water then is 0.025 moles. Now if you think about it, the molar ratio that we saw in the first step of barium bromide to water is 1 to N. So you have 1 mole of barium bromide here, and we have N moles of water. But we have a ratio here of the actual number of moles which are of these substances that we produced in this exact chemical reaction with this specific mass of the hydrated barium bromide crystals being heated to constant mass. So if we take these two numbers and express them as a ratio, the ratio of the number of moles of anhydrous barium bromide to the number of moles of water is 0.0125 to 0.025. If we divide both these numbers by the smaller of the two numbers, we get a ratio of 1 to 2. So this tells us the ratio of barium bromide to water is 1 to 2. So if the ratio as expressed in the equation is 1 to 2, then N must be 2. N equals 2, which means that the formula of the hydrated barium bromide, so the actual formula of hydrated barium bromide is this, Ba, Br2, and the water of crystallization is 2 molecules of water for every formula unit of barium bromide. So now we can answer the question. We can calculate the relative formula mass of hydrated barium bromide crystals. So the relative mass is going to be the relative formula mass of barium bromide plus 2 times the relative formula mass of water. So we have 137.3 plus 2 times 18, which gives us 173.3. So let's move on to the next question. So this is the fourth question. What mass of calcium carbonate is needed to neutralize 2 cubic decimeters of 0.5 molar hydrochloric acid? So again, I'm going to give you a chance to have a go at this one for yourselves. All right, so here's how we do this one. So again, we're starting with the balance symbol equation, which gives us the molar ratio. So the molar ratio, the two substances that we're concerned with here are calcium carbonate and hydrochloric acid. So we see here that the molar ratio is 1 to 2 between these two substances. So on to the second step. We've got enough information here to calculate the number of moles of hydrochloric acid. We have the volume of hydrochloric acid solution and we have the molarity. Remember, this big M means moles per cubic decimeter, the concentration. So since we have the volume and the concentration, we can calculate the number of moles of hydrochloric acid. So number of moles is equal to concentration times volume, which is 0.5 times 2, which is 1 mole. So we have 1 mole of hydrochloric acid. Now the ratio of calcium carbonate to hydrochloric acid is 1 to 2. So if we have 1 mole of hydrochloric acid, we must have half that many moles of calcium carbonate. So third step, number of moles of calcium carbonate is going to be 0.5 moles. So the final step, the fourth step, we're being asked for the mass of calcium carbonate, so we need to convert this number of moles into a mass. So we need the relative formula mass of calcium carbonate, which is going to be 40 for the calcium, plus 12 for the carbon atom, plus 16 times 3 for the 3 oxygen atoms, and this gives us a relative formula mass of 100. So if the relative formula mass is 100 and the number of moles of calcium carbonate that we have is 0.5 grams, we need this equation. We need number of moles is equal to mass divided by relative mass. We need to find the mass, so we rearrange the equation and we get mass is equal to number of moles times relative formula mass. So we have 0.5 moles times the relative formula mass of 100, which means we need 50 grams of calcium carbonate. So let's try the next one. So again, this was a slightly more challenging one that caused some problems for some of you. So have a go at this one for yourselves. We have a 0.1575 gram sample of ethane dioic acid crystals, which have this formula. Again, we have a water of crystallization here. This is dissolved in water. Now in a titration, 25 centimeters cubed of this solution of acid reacted with exactly 15.6 centimeters cubed of 0.16 molar sodium hydroxide. Calculate the value of the relative formula mass of the acid and the value of N. So in this case, we're dealing with a titration. Now, we're going to be looking at titrations in more detail in a later lesson of this course, where we look at analytical techniques. But you probably will encounter many of these titration type calculations. And so a titration is basically an experimental procedure where you are doing a known reaction between two substances in solution, and one of those substances has a known concentration. You measure the amount, the volume of that known concentration of that substance required to completely react the other substance which has an unknown concentration. But the approach is exactly the same as we saw before. So again, I'm going to pause and let you have a go at this one for yourselves. See what you can come up with for this one, and then we'll go through the solution. All right, so let's walk through how we go about this. So once again, we start with the balance symbol equation, which gives us the molar ratio of the substances in question. Now, the substances in question are ethane dioic acid and sodium hydroxide. So we're only concerned with these two. The molar ratio is 1 to 2. So that's our first step. Our second step is to calculate the number of moles of any of these two substances, whichever one we have sufficient information for. So we're being told that 15 centimeters cubed of a solution of sodium hydroxide, which has a concentration of 0.16 moles per decimeter cubed, was required in this chemical reaction. So from that information, we have a volume and we have a number of concentration. We can use this expression, N, number of moles is equal to concentration times volume, to calculate the number of moles of sodium hydroxide that reacted in this titration. So the first thing that we need to do, though, is be aware that the volume is being given in centimeters cubed, and the volume that you put into this equation should always be in decimeters cubed, unless you have a reason to do otherwise. So if there are 1,000 centimeters cubed in every decimeter cubed, then to convert this into decimeters cubed, we need to divide by 1,000. So this volume is 0.0156 decimeters cubed. So now that we have that volume and we have the concentration, we can calculate the number of moles of sodium hydroxide that reacted in this titration. We have 0.16 moles per decimeter cubed, the concentration, times the volume in decimeters cubed. So this gives us a number of moles of sodium hydroxide of 0.002496 moles. So I'm using a rather large number of decimal places here, just so that we don't propagate errors into our calculation. As a general rule, until you reach the answer of a multi-step calculation problem, you shouldn't really round up or down unless you're dealing with an absurd amount of decimal places. So we have the number of moles. We can move on to step 3 now. We can look at the molar ratio between these two substances, 1 to 2 of ethane dioic acid, hydrated ethane dioic acid to sodium hydroxide. So if we reacted 2 moles of sodium hydroxide, we must have reacted 1 mole of this. If we reacted this many moles of sodium hydroxide, we must have reacted half that many moles of this. So we can now deduce the number of moles of ethane dioic acid. It's going to be half this number. So the number of moles of ethane dioic acid is this number divided by 2, which gives us 0.001248 moles. Now we get to the final step. Now in this case, there's a slight wrinkle here because we're dealing with a substance which we don't know the relative formula mass of, because there's a water of crystallization involved and we have a number of moles here. However, in this case, we know that this substance was dissolved in water. So however much of this mass of the hydrated ethane dioic acid crystals was water doesn't really matter, because we know that when we dissolve it in water, those water molecules are just going to go off and become part of the solvent. What we've just worked out here is the actual number of the ethane dioic acid molecules themselves, which reacted with this many moles of sodium hydroxide. So this is the number of moles of ethane dioic acid molecules in this original sample that actually participated in the chemical reaction. So let's go ahead and calculate the mass of ethane dioic acid crystals which reacted. Now this will be part of this mass. It will be some fraction of this mass, and the remainder of it will be water molecules. So if we take the relative formula mass of ethane dioic acid, it's going to be 2 for the 2 hydrogens plus 2 times 12 for the 2 carbons plus 4 times 16 for the 4 oxygens. So this is the relative formula mass of anhydrous ethane dioic acid. That is to say, ethane dioic acid where you don't have water molecules associated with it. So this gives us a relative formula mass of ethane dioic acid of, let's see, I worked it out earlier. What was it? 90. There it is. So we now have enough information to calculate the mass of anhydrous ethane dioic acid that reacted with the sodium hydroxide. So the mass is going to be the number of moles times the relative formula mass. This is going to be 0.001248 moles times 90. And this gives us a mass of ethane dioic acid of 0.11232 grams. So this is the proportion, this is the portion of the hydrated ethane dioic acid which was only made up of ethane dioic acid molecules. So now, if we know that the hydrated sample mass was 0.1575, and we know that the anhydrous mass is 0.11232 grams, we can just subtract 0.11232 grams from 0.1575 grams to find what proportion of this mass was the water of crystallization. So the mass of water of crystallization is going to be 0.1575 minus 0.11232, and this gives us 0.04518 grams. So this is the mass of water of crystallization that was present in the original hydrated sample of ethane dioic acid crystals. So if we now want to work out the value of N, and therefore the relative formula mass of the hydrated crystals, we can now use this mass of water and the relative formula mass of water to calculate the number of moles of water molecules in this sample of the water of crystallization. So the number of moles of water molecules in this mass of water is going to be 0.04515 divided by the relative formula mass of water, which is 18. So this gives us a number of moles of water of 0.00251 moles. So now we have the number of moles of water and we have the number of moles of anhydrous ethane dioic acid crystals. So N is the ratio, is the number of water molecules there are for every one molecule of ethane dioic acid in the hydrated crystals. And so therefore, the molar ratio of ethane dioic acid crystals to water, we can now use this to calculate the value of N. So in the hydrated crystals, we can say that the ratio of ethane dioic acid to water is 0.001248 to 0.00251. Now, if we divide both these numbers by the smaller of the two numbers, we see that this simplifies to approximately 1 to 2. So therefore, we can take this and say that the formula of the hydrated crystals must therefore be H2C2O4.2H2O, which is to say that every molecule of ethane dioic acid in the hydrated crystals will be associated with 2 molecules of water. So N is 2. So we can now calculate the relative formula mass of the hydrated crystals. So the relative formula mass is going to be the relative formula mass of the anhydrous ethane dioic acid that we worked out over here is 90, plus 2 times the relative formula mass of water, which is 18. And so this gives us a relative formula mass 126. So let's have a look at a problem involving gas volumes now. So what volume of carbon dioxide gas is produced at room temperature and pressure from the complete thermal decomposition of 500 grams of calcium carbonate? Again, we're being given the balance symbol equation here. So have a go at this one and we'll look at the solution in a moment. All right, so this one is, you'll be glad to know, relatively straightforward compared to the last one. So what we have here is a situation where it's the same approach. You start with the balance symbol equation. This gives us the molar ratio between your two substances. So here we're concerned with trying to work out the volume of carbon dioxide gas from the amount of carbon dioxide we're starting with, calcium carbonate that we're starting with, which is 500 grams. So the two substances in question are this one, and we can see that the molar ratio is 1:1. So our next step would be to use the information that we have available to us to calculate the number of moles of any one of the substances involved in the chemical reaction. So in this case, we have 500 grams. We have a mass of calcium carbonate, and we have a periodic table available to us, so we can calculate the relative formula mass of calcium carbonate, which we calculated before. It's 100. And so we can now calculate the number of moles of calcium carbonate, and this is our step 2. So number of moles is equal to the mass divided by the relative mass. We have 500 grams. We're dividing by a relative mass of 100, so this gives us 5 moles. This is the number of moles of calcium carbonate that we're starting with. So now we can use the molar ratio to deduce the number of moles of the substance in question. So if the ratio is 1:1 and we're starting with 5 moles of this, we must be producing 5 moles of this. So the number of moles of carbon dioxide being produced is 5 moles. So the final step is to use whatever is the appropriate equation or relationship to solve the question. In this case, we're being asked what volume, not the number of moles of calcium dioxide produced, but what volume of carbon dioxide produced, but what volume of carbon dioxide is being produced, and it's at room temperature and pressure. So in this case, we use the molar gas volume. Any 1 mole of any gas at room temperature and pressure will occupy 24 cubic decimeters. And so therefore, the volume of carbon dioxide that we're going to produce is going to be the number of moles 5 multiplied by the molar volume, which is 24. And this gives us 120 cubic decimeters. So let's have a look at one final one about gas volumes here. So what mass of calcium reacts with 72 cubic decimeters of oxygen at room temperature and pressure? So here we have the equation. Have a go at this one for yourselves, and then we'll go through the solution. All right, so this time, again, we approach it the same way. We're starting with the balanced symbol equation. We are being given, we're being asked about the mass of calcium, and we're being given the volume of oxygen that we're reacting it with. And so these are the two substances in question. And as we can see, the molar ratio is 2 moles of calcium reacts with 1 mole of oxygen gas, 2:1. So the second step is to work out from the information given the number of moles of any of the substances involved. So in this case, we have the volume of oxygen gas, and we're being told it's at room temperature and pressure. So we know that any 1 mole of any gas is going to occupy 24 cubic decimeters at room temperature and pressure. So from this information, we can calculate the number of moles of oxygen gas that we have. So in this case, the number of moles of oxygen gas is going to be the volume divided by the molar gas volume. So this is going to give us 3 moles. So third step is to use the molar ratio and the number of moles of whichever substance we calculated to deduce the number of moles of the substance in question, which is calcium. So if 1 mole of oxygen gas reacts with 2 moles of calcium, then 3 moles of oxygen gas will react with 6 moles of calcium. So the number of moles of calcium is 6 moles. So the final step is to use the appropriate equation to calculate the answer to the question. In this case, we're being asked not for the number of moles of calcium, but for the mass of calcium. So we're using this expression here. Number of moles is equal to mass divided by relative mass. Mass in grams is going to be therefore equal to the number of moles times the relative mass. Relative atomic mass of calcium is 40, and so the mass of calcium that we need to react with 72 decimeters cubed of oxygen is going to be 6 moles times 40, which gives us 240 grams. Okay, so hopefully that clarifies some of the questions that some of you have been asking, and also hopefully that shows you how we would apply this kind of approach and the ideas that we've already encountered in the lessons of this topic to solving some more challenging and some slightly easier exam type questions. So that's going to do it for the recorded part of this lesson. I hope that was useful to you. I'm going to go into the Q&A discussion now with the students that I have in attendance with me. Thanks for watching, and I'll see you in the next one. Take care.